Let's start with a definition. A vector with initial point at the origin in our rectangular coordinate system is a position vector. Here's a picture for you to consider. We have vector u in the rectangular coordinate system. I'd like to highlight that the initial point is at the origin in our plane, which makes it a position vector. And also, actually, what I want to add to the picture here is angle theta that is formed by the positive x-axis and the vector. I want you to notice that every vector every position vector in the real plane corresponds to an ordered pair, a comma b, right? So where vector u terminates in the plane is at an ordered pair a comma b. So therefore, while geometrically a vector is a directed line segment, here in this section, we are considering a vector as an ordered pair, okay? And you can see we're writing our vector with this special notation. You can see that there's two components. A here is called the horizontal component, and B here is called the vertical component. So you have two components for every vector. And I don't want us to lose the fact that this vector is called a position vector. Its initial point is at the origin, like we already said, and the terminal point is at the ordered pair a comma b, so which is the reason why we use this special notation for identifying a vector. All right, I have some more terminology for us. Magnitude and direction angle of a vector a comma b. The magnitude or the length of a vector named u is found by the following. We use these absolute value bars to denote magnitude of a vector. So the magnitude or the length of this vector is the square root of a squared plus b squared. Now, you can see how this ties into the Pythagorean theorem. The length of this vector is basically the hypotenuse of this right triangle that is formed here, right? So the length or the distance here from the initial point to the terminal point is basically the hypotenuse, which can be found using the Pythagorean theorem, the square root of a squared plus b squared. Furthermore, we have the direction angle theta, which is here, has to satisfy the following. Tangent of theta is equal to b over a. I just couldn't, I struggled to find theta on this app I'm using, so I don't want you to get, confused. Tangent of theta is b over a, okay? I wrote out theta in words here, but this is really what we mean. Of course, this is only defined when a is not 0, right? Okay, guys, let's look at this first example. Find the magnitude and direction angle for vector u, which is defined as -5, 4. -5 is the horizontal component, and 4 is the vertical component. All right, so let me move the screen up a little bit for us here. We know that the magnitude of our vector, the magnitude of vector u is equal to the square root of a squared plus b squared, which are your components. So the magnitude or the length of our vector is going to be equal to the square root of -5 squared plus 4 squared. So which just gives us the square root of 25 plus 16, which is 41. So that's pretty straightforward. That part is done. Magnitude found. The length of the vector is the square root of 41 units. Now, the other thing that they ask us to find is the direction angle. Now, the direction angle theta, let's call it, must satisfy that tangent of theta equal to b over a, which in this case, now remember guys, this is your b right here, 4, and a is -5. So then this is going to be +4 over -5, or -4/5, okay? Now what I'm going to do right now is take my calculator and use the inverse tan button. And I'm getting about -38.7 degrees if I round to the nearest tenth, okay? Now, this cannot be my answer because allow me to draw a picture for us really quickly. -38, let's just say about -39 degrees, okay, if you don't mind. -39 degrees is, I don't know, somewhere right here, correct, everybody? Negative 39 degrees. But the problem with that is, look at your components. You have a negative horizontal component and a positive vertical component. Think about it. A negative horizontal component and a positive vertical component. That must put us in quadrant number 2. But a negative horizontal component, positive vertical component has to be in quadrant 2. So how do I go from quadrant 4 to quadrant 2? Let's just add 180 degrees to negative 38.7 degrees, and it'll jump us over here in quadrant 2. Again, here's a visual of what I'm mentioning. Our calculator gave us this vector here, which is in, or it gave us this angle here, which is in quadrant 4, but we can't be in quadrant 4 with these components. So we add 180 degrees to get its supplement over here in quadrant 2, which when I add 180 degrees to negative 38.7 degrees, like this, I am getting that theta is about 141, I'll round to the nearest tenth, 141.3 degrees, which makes sense because that's in quadrant 2. That agrees with my components. So I cannot stress enough that when you are finding your direction angle, please take close note as to which quadrant you are in. How do you tell which quadrant you're in? By the signs of your components. Okay, now how do I find, so they gave me the components and then we found the magnitude and the direction. Now what if it's the other way around? If I know the magnitude and the direction angle, can I find my components? And the answer is yes. So the horizontal and vertical components respectively of a vector u having magnitude absolute value of u and direction angle theta are the following. A, which is your horizontal component, is the product of the magnitude of your vector and cosine of angle theta, which is your direction angle. While B, your vertical component, is a product of your the magnitude of the vector and sine of the direction angle. Okay? Check this out. Vector V has magnitude 14.5 and direction angle 220 degrees. Find the horizontal and vertical components. Now, let us find A, the horizontal component. A is the product of the magnitude, which they gave us as 14.5, and cosine of the direction angle, which in this case is 220 degrees. Now, I already know that my horizontal component is going to be negative. How do I know that? Well, 220 degrees is in quadrant 3, and cosine is negative in quadrant 3. So this is going to be a negative value times a positive magnitude, so this whole value is going to be negative. All right, so when I punch this into the calculator, I am getting approximately negative 11.1. Cool? Let us find now the vertical component. The vertical component is similar. It's 14.5 times sine of 220 degrees. Now, again, it's still going to be negative because sine is also negative in quadrant 3. And okay, I'm getting B is about negative 9.3. Okay, so then my answer for the components is the following. So we have this vector V, right? And it has these components, negative 11.1 approximately, comma, negative 9.3. I'm using the special vector notation, okay? All right, check out the next one. Write each vector in the form A comma B, special vector notation there. This first vector, they've given you the magnitude as of 8 and direction angle 135 degrees. 135 degrees is in quadrant 2. That tells me that the horizontal component is going to be negative and the vertical component will be positive. So we know that vector u will have the horizontal component. We call it A, which is the product of the magnitude and cosine of the angle, comma, the vertical component will be the product of the magnitude and sine of the direction angle. Okay, so then the components will be 8 times, now cosine of 135 degrees is just the opposite of cosine of 45 degrees, so it'll be negative root 2 over 2, comma, 8 times sine of 135 degrees is exactly equal to sine of 45 degrees, which is just root 2 over 2. Okay, so simplifying here, your components are negative 4 root 2, comma, positive root 2. All right, that's the form they want us to write the vectors in. All right, first one done. Let's go for another. Check out this next one. Vector v has magnitude 4 and direction angle 270 degrees. All right, so let's do it together. So vector v will have this notation. The first component will be the horizontal component, which will be the product of the magnitude and cosine of your direction angle. The vertical component will be the product of your magnitude and sine of your direction angle. So like that. So then it'll be 4 times cosine of 270 degrees is 0, comma, 4 times sine of 270 degrees is negative 1. So then the notation for vector v will be 0, comma, negative 4. Cool. All right, this example shows how we can operate on vectors. That is to say, it shows vector operations. So they've given us two vectors here, vector u, which is identified as negative 2, comma 1, and vector v, which has components 4, 3. We need to find and illustrate each of the following. Let's do this one at a time. Let's find u plus v, and then we'll illustrate it, all right? Okay, everybody, I have vector u written on the board and vector v also on the board. Now, I bet you can take a really good guess at how we're going to illustrate our, how we're going to add our two vectors. You could probably guess we're going to add like components. So this horizontal component plus this horizontal component, and then this vertical component plus this vertical component, which will give us the components negative 2 plus 4, which is 2, comma 1 plus 3, which is 4. So there's the sum. All right, let's draw a picture to illustrate this. What I want to do is I want to illustrate vector u first. Now remember, vector u has all of these are position vectors. So the initial point is at the origin, and the terminal point of your vector terminates at the ordered pair negative 2, comma 1. So therefore, vector u is something like this. All right, negative 2, comma 1. That's where it terminates. Vector v is also a position vector. Again, initial point at the origin, terminal point, this time at the coordinates 4, comma 3, which of course is quadrant 1. So there's 4, comma 3 about right there. So there is my vector v. Okay, maybe I should be labeling this. This would be a good idea, right? So this is vector u over here. This is vector u, vector v. And now let me draw you or illustrate vector u plus v, right? Which is coordinates 2, comma 4. Okay, so 2, 4 will be about right there. So there is my vector u plus v. Cool? What a nice drawing, isn't it? All right, let's go to part B and C now. For part B, it says to take vector u and multiply it by negative 2. Okay, so when we do that, I have vector u already written with a scalar of negative 2. This is equal to multiply each component by negative 2. That'll give you positive 4, comma, negative 2. All right, to illustrate this, I already have vector u on the board. We plotted that last time. So vector u. Now we want to get vector -2 times u, which has coordinates or terminates at coordinates 4, -2, which is about right here. So here is -2 times u. All right? All right, one more to do, guys. 3u minus 2v. Okay, we got 3 times vector u minus 2 times vector v. Let's do it. When I multiply each of the components of vector u by 3, I get -6, comma 3. And then minus, when I multiply each of the components of vector v by 2, basically when I double them, I get 8, comma 6. Now when I add like components, I get -6 plus, or -6 minus 8, excuse me, -14. And then 3 minus 6, which is -3. This vector 3u minus 2v will be a position vector. The initial point at the origin and the terminal point at the ordered pair -14, -3, which we all know is quadrant 3. So then this would be the illustration of 3 minus 2v. Now to wrap this section up, we want to talk about the dot product between two vectors. This is really important. The dot product of two vectors u and v, where u is defined as a comma b and v is defined as c comma d, is denoted as, now let me show you what the dot product is. This is how you write it first of all. It's u dot v, so this is not multiplication, and it's defined to be a times c plus b times d. Okay? It's basically the sum of the products of the horizontal components and the vertical components. What's really important is that you and I understand that the dot product of two vectors is not a vector. It's actually just a real number. Sometimes it's called the inner product, and it's used for a lot of things, but the main thing that you and I will use it for in our class is to find the angle between two vectors. So look at this example. Find the dot product between these two vectors, or of these two vectors. Now the dot product is going to be equal to the sum of the products of their first components, called the horizontal components, and their second components, which are called their vertical components. In other words, it'll be equal to -5 times -2 plus 2 times -4, okay, which is +10 minus 8. So the dot product of these two vectors is 2. Cool, that was simple enough. Let's check out another one. So here we have 10, comma, -1. That's one vector, dot, +1, +10. Let's find the dot product of these two vectors. Now, it'll be equal to 10 times 1 plus -1 times 10. So it'll be 10 minus 10, which is equal to 0. So the dot product of these two vectors is just 0. Now what's really important to note is that the dot product of two vectors can be positive, like we got in example 5, part A. It can be 0, like we just finished getting, or it can be negative. Now the sign of the dot product, whether it's positive or negative, or even if it's 0, tells us something about the angle that is between the two vectors. Okay, what I want to show you now is how the dot product, if it's positive, tells you that the angle between the two vectors is acute. If the dot product is 0, then the angle between the two vectors is a right angle, 90 degrees. And if the dot product is negative, then the angle between the two vectors is obtuse, something between 90 degrees and 180 degrees. So let me show you how that is derived now. So here's a geometric interpretation of the dot product. I have two position vectors, one named u and the other one named v. And here is vector u, which terminates at a sub 1, a sub 2, and vector v, which terminates at b sub 1 and b sub 2. The angle between the two vectors is theta, and we're going to show how the dot product can help us find the angle between those two vectors. Now this angle theta is an angle that is between 0 and 180 degrees. Okay, so I can use the law of cosines. If I start from this terminal point and go to this terminal point here, draw that vector there, then the law of cosines will lead me to the following. Now what I've done here is, oh, by the way, I've labeled this vector here, which has its initial point at the terminal point of vector v, and its terminal point at the terminal point of vector u. I've named it w. Now, the law of cosine says the length of this vector, basically its magnitude, quantity squared, is equal to the length of this vector, u, quantity squared, plus the length of this vector, v, quantity squared, minus 2 times vector u times vector v times cosine of our angle theta, which is opposite this vector w. Now, the magnitude of vector w, that is the length of its vector, of this vector, can be found using the distance formula, right? So then this is going to be equal to the square root of, now, this terminal side here, terminal point, excuse me, of vector w terminates at a sub 1, a sub 2. So the distance formula will say this x coordinate, a sub 1, minus b sub 1, the other x coordinate, quantity squared, plus, and then it'll be this y coordinate, a sub 2, minus b sub 2, quantity squared. This here is the distance of the length of vector w, its magnitude, that is to say. But don't forget that this is being squared now, all right? That's being squared. Now this is all equal to, now I'm pretty sure I'm going to have to move this up here and create some space. Now what comes next on the right side is the magnitude or the length of vector u, right? Quantity squared. So I'm going to use the distance formula again, but it'll be a little simpler this time because it'll be a sub 1 minus 0 quantity squared and a sub 2 minus 0 quantity squared. In other words, it'll simply be the square root of a sub 1 a sub 1 squared plus a sub 2 squared, right? And then of course we're squaring this. Now hang tight as I'm eventually going to have to move this down even more, okay? Plus, I'm going to have to come down here, guys, so excuse me. So plus the magnitude of vector v quantity squared. Now again, it'll be b sub 1 minus 0 quantity squared, and then b sub 2 minus 0 quantity squared. Okay, so it'll be the square root of b sub 1 squared plus b sub 2 squared. And don't forget the square of this, right? Minus. Now for all of this, folks, I'm asking that you just write it down again, all right? Copy it down. 2 times the absolute value of u, or the magnitude of u, times the magnitude of vector v, times cosine of angle theta. All right, so this seems like a lot. This is the left-hand side of your equation, and all of this is the right-hand side. Now, this is all by the distance formula so far. I'm going to move my screen up, and we're going to end up losing this picture, okay? But don't forget, we're doing all of this to figure out how the dot product helps me find the angle between two vectors. Okay, guys, I moved it down, and I put this blue bar here just to separate my work, all right? So here, I'm going to work on this here on the left-hand side. When we square the square root is gone. And in addition to that, I'm also going to expand these binomials here being squared, okay? So when I expand them, I get a sub 1 a sub 1 squared minus 2 times a sub 1 b sub 1 plus b sub 1 squared. Okay, that was expanding this binomial. Now I'll expand this binomial, which gives me a sub 2 squared minus 2 times a sub 2 b sub 2 plus b sub 2 squared. All right, all of that is just this part on the left-hand side. Now, the right-hand side, let me say, is equal to, now what I'm writing now is the right-hand side of the equation. When you square the square root, this square root here, this is gone, okay? And you're just left with a sub 1 squared plus a sub 2 squared, all right? Plus, now I'm over here, this square root is now gone because of the squaring, and you're left with b sub 1 squared plus b sub 2 squared minus 2 times the magnitude of vector v times the magnitude of vector, minus 2 times the magnitude of vector u times the magnitude of vector v times cosine of our angle theta. All right. Now notice that you got a sub 1 squared on the left and an a sub 1 squared on the right, so they cancel. Furthermore, a sub 2 squared on the left and a sub 2 squared on the right cancel. In addition, b sub 1 squared on the left and b sub 1 squared on the right. B sub 2 squared on the left, b sub 2 squared on the right. Now that leaves me with negative 2 a sub 1 b sub 1 minus 2a sub 2 b sub 2. That's all I'm left with on the left is equal to negative 2 times the magnitude of vector u times the magnitude of vector v times cosine of angle theta. Now what I would consider or suggest for you to do is to divide both sides by negative 2. All right? And what that would give us now is, now on the right, I'm going to write this down first, okay? I'm going to get the magnitude of vector u times the magnitude of vector v times cosine theta is equal to this left-hand side, which turns out to be a sub 1 b sub 1 plus a sub 2 b sub 2. Now, look at this now, and does this look familiar to you? A sub 1 was the horizontal component of vector u. B sub 1 was the horizontal component of vector v. A sub 2 and b sub 2 were the vertical components of vectors u and v. In other words, and if you allow me to, maybe this will help you, just reference the picture that we had in the very beginning of our entire argument. There it is. A sub 1 times b sub 1 is what we have, plus a sub 2 times b sub 2, right? And we've already defined that in our work as u dot v. That's what u dot v is, how it's defined, right? That's the dot product between, this right here is the dot product between my two vectors, all right? So now, if you would divide both sides by the product of the magnitudes of your vectors, you will get the following very important statement that says that cosine of the angle between the two vectors is equal to u dot v divided by the product of their magnitudes. Look at that. I'll say that one more time. The cosine of the angle that is between two vectors is equal to the quotient of the dot product of the two vectors and the product of their magnitudes. You may want to box this in your notes. Now, I hope that this shows you how my explanation earlier, my reasoning earlier about the sign of your dot products tells you something about your angle theta. That is to say, if the dot product of two vectors is positive, then that means this whole right-hand side, this fraction, will be positive because the magnitude is defined to be the square root, the principal square root. So the denominator is always going to be positive, but the numerator can be positive, 0, or negative. The dot product, if it's positive, then the whole right-hand side will be positive, and cosine is positive. Cosine of an angle is positive if that angle is in quadrant 1, meaning it's acute. If the dot product is 0, then this whole fraction will be 0, so the whole right-hand side will be 0, and cosine of an angle theta will be 0 if and only if that angle theta is 90 degrees. Finally, if u dot v, if the dot product is negative, the whole fraction is negative, and we know cosine is negative in quadrant 2, which puts theta in quadrant 2, which means it is obtuse. Here, this summarizes it really nicely. If the dot product is positive, the angle between the two vectors is acute, meaning it's between 0 and 90 degrees. If the dot product of two vectors is 0, then the angle between the two vectors is 90 degrees, or a right angle. And if the dot product is negative, then the angle between the two vectors is obtuse. That is between 90 degrees and 180 degrees. And one last thing before we look at the last example. If the dot product is 0, then the angle between the two vectors is a right angle. In this case, the two vectors are said to be orthogonal. Two vectors are orthogonal if their dot product is 0. Two vectors are said to be orthogonal if their dot product is 0. That is to say, two vectors are said to be orthogonal if the angle between them is 90 degrees. That's very important. All right, check this out, guys. Find the angle between the two vectors. One of them is u, which is 5, negative 12, and the other one is v, which is 4, 3. All right, so what we know is that cosine of theta, now let's consider theta to be the angle that's between the two vectors, will be equal to, now the numerator will be u dot v, so it'll be u dot v. That'll be just my numerator, okay, the dot product between the two vectors. And my denominator will be the magnitude of vector u times the magnitude of vector v. Now remember what the dot product of two vectors is. It'll be 5 times 4 plus negative 12 times 3. So here I have the dot product in the numerator that I just called out. And then here is the, this is the magnitude, forgot that word for a second, the magnitude of vector u, and this is the magnitude of vector v. All right, so then the numerator will be 20 minus 36, which is negative 16. Right there, everybody. Stop right there. The dot product is negative. That tells me that the angle between my two vectors is obtuse. All right, cool. Let's continue with this denominator. I have the square root of, let's see, this is 25 plus 144, so that's 169. Okay, times the square root of 16 plus 9, which is 25, like this. So then this gives me negative 16 over 13 times 5. So then cosine of angle theta will be equal to negative 16 over 65. Cool? All right, now we can use an inverse trig function to say that theta, which is the angle between my two vectors, is, let me make that a little nicer there, theta is equal to inverse cosine of negative 16/65, which I'm getting approximately equal to 104.25 degrees. I just rounded to the nearest hundredth, okay? So this, ladies and gentlemen, is the angle between those two vectors. Isn't that great? And it is obtuse, right? It's more than 90 degrees, just like we predicted. Let's do this again. Here's the next one. Actually, this is the last example. We have two brand new vectors, u and v, and we want to find the angle between them. All right, so we know that cosine of theta, which we're calling the angle between the two vectors theta, will be equal to u dot v divided by the product of the magnitudes of those two vectors, which would be equal to, all right, guys, this is what I get. This is u dot v upstairs, and then downstairs I have the product of the magnitudes of the two vectors. All right, okay, let's simplify this. Cosine of theta is equal to, up here I get 24, watch this, 24 minus 24, and down here I get the square root of 16 plus 9 times the square root of 36 plus 64. Okay, ladies and gentlemen, please notice that your numerator is 0. At this point, when I'm doing this work, I stop. I don't do this any further because I already know the right-hand side, the entire right-hand side will be equal to 0. Whenever the fraction, the numerator is 0, the whole fraction is 0. If you want to keep going, by all means you can, but you're just going to get 0 over 50. That is to say cosine of theta is equal to 0, and that only happens if, so that implies that theta is 90 degrees. Okay? I don't even need my calculator for this problem here. Now, what's really important that you and I acknowledge is that u and v are said to be orthogonal. So u and v are orthogonal because the angle between them is 90 degrees. But again, guys, once I find that the dot product is 0, I stop right there and say 90 degrees, all right? 90 degrees, or right angle. It's a right angle, all right? Cool deal.